board, school board, whatever you call that. So I will make sure they're not voted in again. For darn sure, because I'm mad, right? It's only when you're mad does action come. So I hope you're mad, a little bit mad, because the exam is 1 week from today. So now if you provide some action to that madness, you'll do well on the exam, right? No one's following my reasoning here? Nobody likes that reasoning? I think it's pretty darn good reasoning, if I say so myself. Okay, so I am happy to go over, so I'm looking for my chalk. I have to hide it. Okay, so I'm happy to go over the homework. Are there specific questions that we have about the homework? Or do we just want to say, do it all? Like, I don't know where you're at, so I need some feedback here. Yeah. The products from part 2, the NMR problems. Okay, so we have a call for the NMR problems. There's A and B, we can do those. How do we do on problem 1? Okay? Okay, problem 1 was fine? Okay, we'll see how that goes in grading. I am going to go over a couple in 3. And 4, you're going to be pretty mad about some of it, so I'll do some of 4 too. Let's start with 2 then. So if 1 was fine, we'll start with 2. So one of the homeworks would be
sneaky molecules.
So this should be what you got, okay, for the NMRs. So to start with, B was hard. I know B was hard, and a lot of people were having a hard time with B. You need to remember first, though, to do your IHD, and the minute you see an IHD of 1, you guys are automatically at double bonds. You've got to remember about your rings, okay, because that's where trouble comes. I'm sure you all came into this in the end, but I'm here to remind you. Don't forget, rings are also a valid IHD, right? A ring or a double bond. The second thing about this is the symmetry in the system, which I recognize because I have really only 2 unique environments and lots of hydrogens, right? So that really speaks to symmetry to me. I can't have a 2-part symmetry, though, right? Because a 2-part symmetry, I wouldn't have a peak that would have 9 hydrogens, right? So it had to be a 3-part symmetry. Does everyone know what I mean about that? Okay, so there was one peak on here that had 9 hydrogens, right? If you looked at the NMR for that B, you had one that had 9 hydrogens. This actually was a doublet, but it's very hard to see. And then there was a quartet, which I've spread out a little bit. This one is a little bit easier to see, though, because you can see the differences in heights. But my point is that if there's symmetry, which you know there has to be, because there's only 2 unique environments and 12 hydrogens, right? So it's a lot. You can't have a 2-part symmetry, because a 2-part symmetry would say, in essence, I have 4.5 protons here and 1.5 protons here. I can't have a half proton. So it has to be a 3-part symmetry, right? That's just using logic. And so that's telling me then that I have 3 hydrogens here and 1 hydrogen in each symmetric unit, which is how you would have wound up at this, okay? So when you came and did the mechanism... Before my interview, I went to get something out of the dryer, and I opened the dryer, and a bird came flying out, right? And a dryer, yes. Always put cages on the outside of your dryer vents. If I can teach you anything in organic chemistry, everyone write this down. Always put a cage on. I don't know what to do about the damn bird. Kim, can you call animal control or something? There must be a University of Maryland animal control. Oh, wait, we have a pre-vet in here. What are we going to do with this bird? You want to be a vet? Who do we call?
Cover your head for
So what can we do? Oh, open that door! Someone open that door back there! Can go out.
It's an emergency.
It's not a line.
It's an emergency.
It's gonna be a good recording I've ever had.
Okay.
I didn't even know
Hold on.
looked at me and I was like,
Scream my video.
Oh yeah, that's going online.
You should send this to me. Going on.
I want to see
Okay. All right. This is highly disruptive, I realize, but just every time the bird comes towards you, just duck. Get out of here. I don't know what else to do. I got to teach organic chemistry. So, I love that some of you have your video cameras out. I don't know what that's going to do. All right. Let's find some, modicum of decorum here. Okay. When you hydrolyze these guys back, you should have come back to a bunch of aldehydes and then likely something like this, which actually should have been an aldehyde as well, right? But so in the end, you should have had 3 of these and water, and 1 mole of water. But if you have 2 of these and 1 of these, I'm okay with that. Does everyone understand what I mean? Should I write it out more clearly, or do you understand? Are there questions about that? Yes. If we're doing out the whole mechanism would be hard, but here, you can either have 3 of these and 1 water, or you can have 1 of these and 2 moles of this. It's really what I'll accept as final answers. Yes?
Didn't the bottom right, didn't that end up being like an aldehyde?
It is. That's what I'm saying. This converts into the 3rd mole of this and 1 mole of water. Okay? Does everyone understand what I mean? Yes. The water is there. Yes.
So how many points? How many points does a water count
I
for?
have no idea. Everyone wants to know points. Tell me the number of points. I want to know the number of points. Okay.
Well.
This would have wound up being formaldehyde and then some diol, right? 3 carbons intervening. Is this what we got? Yeah.
Wouldn't you have a hydrate shift then the moment it opened up? There would be a primary carbon-cation. Yes. Would there be a hydrate?
Okay, if you thought of a hydride shift, that would be okay too. Sure, I will take the hydride shift in that one. Yes, I understand where you're going with that. Yes. Okay. Are there any other questions about 2? If you have them, come on up and tell me. Does anyone have a sight on the bird? Where is the bird? Okay, very good. Just making sure that, because I want to know where to duck from. Thank you. You just tried to get me worked up. I'm already sweating. It's okay. I'm sure this is joyful for you. Watch my organic chemistry professor scream. Who brought the bird?
I think it was just the late April 1st. It finally came out, finally. 3 days later, I forgot about
Okay, I'm going to take 2 answers here. 2 answers here. One of them, actually, you can even get to this water. So I'll take this. I'll even take that deprotonated. That's fine. This reaction is reversible. Okay? This is a hydration reaction. It is a fully reversible reaction. This is very confusing, I recognize. And the reason it's on the homework, you could have gone into the chapter, you could have looked it up. The truth is that hydroxide can be a leaving group when you're in basic conditions. So if you're within conditions that have OH minus can actually be a leaving group. That's very, very confusing, and it happens seldom. Note my specific requirement for that. When you're in basic conditions, OH minus can be a leaving group, which makes this reaction reversible. If instead you show me some acid-base chemistry, you actually pull from here, but that's fine. You can also get credit for that, and this is also a reversible reaction, which is one that we talked about last class. Because truthfully, OH minus can do both things. It can hydrate, which forms the top product, okay? The deal is, though, if you looked at this equilibrium, you would find that the equilibrium sits itself far to the left, okay? If you actually looked at a KEQ for those reactions, you'd find that they're very small numbers, minuscule, which in essence says to me that I really am centered on the ketone or the aldehyde. This is one reason why I haven't really covered these reactions very thoroughly, because they really sit to the keto or aldehyde side, okay? More likely than not, you're going to see an acid-base reaction, which is going to further go on and do aldol, which is something we see 2 chapters from now. Yeah? Yes, and aldol condensation is the next step. If you looked ahead or if you Googled or whatever it is, yes, aldol is the next step. If you got that, then you don't need to come to class for the next month. You're good. Actually, come for the test, though. Yeah, okay. Are there other questions about this one? So I wanted to make sure 2B. So 3B. So the first one in problem 3 was reversible. That one was probably fine. The third one, the lithium aluminum hydrides, the sodium borohydrides, those were also irreversible, right? Both sodium borohydrides. Okay, very good. All right, I think we're good. Let's talk about problem 4. This is where trouble's going to ensue.
First two reversible.
Appreciate it.
Because I've heard it kind of
Yep, screw that up.
So this, in essence, is the right answer set. All right? Because this leads to 2 unique stereoisomers. There is, in essence, not a plane of symmetry that runs through this molecule. Okay? So these groups, these are asymmetric carbons, and, which was your question, right? They're asymmetric carbons, and there is not a plane of symmetry. Okay? So they're not necessarily isomers in terms of RS, right? But they are cis-trans isomers. If you remember, or if you learned very thoroughly, when we talk about isomerism, the first level of isomerism is cis-trans isomerism, of which a subset of that can be enantiomers and diastereomers. So we're not getting into that language down there because of the nature of these molecules. They actually are cis-trans isomers. We could talk about that till we're blue in the face. But I can tell you that if you had 2 wedges or 2 dashes, now you're at a place that there is a plane of symmetry, and that's it's a meso compound, which is achiral, and meso compounds don't have a corresponding enantiomer. Okay? And let's say you decided just to put the methyls in straight lines, right? Just bonds in the plane of the page. I understand that as well, but that's actually saying every time, generally, it's actually not even the right language to do it, but it sort of becomes so commonplace that we don't even talk about it anymore. If you did something like this, this is in essence saying, I'm a wedge or a dash, I'm a wedge or a dash, so you haven't actually specified into this trans of the 2 methyls that is necessary in order to constitute differences in stereoisomers. Yeah?
Are they the same?
These 2? No, they are not. They actually, I know where you're going with this, but they are prochiral, and prochiral things are actually different. We can talk about that. We probably need to talk about it at a different time. Yeah.
If you do the chair confirmation, wouldn't you want the 2 methyls to be axial?
Okay, what is the,
Like for just A, for example?
why would I, to do E2 and yeah. So the very fact is, though, that's a good question, because these, truthfully, I mean, we're drawing them as rings here without drawing their true 3-dimensional structure, which is unfair, and I'm sort of breaking rules here. But suffice it to say that when you go to do this, every isomer has 2 conformers, right? Every isomer has 2 conformers. So regardless if the more stable keeps it equatorial, it might need to ring flip to get to an axial placement for the reaction to happen. That's true, but this is also not an E2 reaction, which is the requirement for E2, but it's rather an E1 reaction. Going from C and D to E is an E1 reaction. An E1 reaction doesn't necessitate that the leaving group be in an axial position. We can talk about anything else about that after class. Okay, are there questions about this? So there's going to be grading in here that we're going to need to look at and talk about. But you're not going to lose a ton of points. If you're getting the frameworks, excuse me, then you're doing pretty good. Are there other questions? Okay, so overall okay? Not okay?
Could you maybe just draw what the end structure was for problem 1?
The end structure, yes. The end structures for 1B was this structure here. Let's think about that. Excuse me, nitrogen, this, 2 carbons, 4 carbons. Okay, so carbonyl 1, 2, 3, 4, this guy, and then, excuse me, off of this guy is an NH2 and a phenyl. And then 1A is different, right? 1A should have been an enamine, and the enamine would have been creating something like this. This is right, 1, 2, 3, yep. So this is my carbonyl carbon, should have a methyl. This actually should be out here then. And this guy is going to be this guy here. Yes? Okay, if you have questions about these, write them down. We can come up after. I mean, I did this in like 30 seconds. See, I'm not doing a mechanism. I'm not being very careful. I'm just drawing them up. What I can promise you is this. First thing I'm going to do when I go home today is write out answer keys. I'll take a picture of them with my phone. Fastest way to do it, deposit that JPEG online. So you'll have answer keys to both the homeworks today, probably tonight at some point. Okay, say by 10 o'clock. I know you're not going to do any work tonight. That's totally fine. Don't do any work tonight. But they'll be there tomorrow when you wake up and you're gunning to do some organic chemistry. Okay? So you can pre-grade your own homework. I will do everything. I'll do all the mechanisms, everything, so you can follow it all along. If you have any trouble, come on into the office on Monday. For now, though, we're going to turn it around and we're going to start talking about carboxylic acids. That's the chapter we're in. Okay? We're almost to the point that we can get on with it. Okay.
You did it again.
Okay, so if you're reading the carboxylic acid chapter is actually in Loudon is probably a good read. It's a very fast read, and so it's a good place to go if you need help with the notes. I know sometimes the chapters can be really intense. They can have lots of stuff in there that isn't important. I actually think this chapter is pretty succinct and actually well written. So if you're interested in reading, because that helps you, by all means, it's a great chapter to go in and look at. Okay? It always starts with things that you should know, physical properties. These are acids. That shouldn't break the boat here, right? We should all know that they're acids. They're called carboxylic acids. Whole section on that. That'll make you feel smart. You know they're acids. The next thing that they'll cover is the nomenclature. And so what you should remember, in last class we were talking about this, we've now reached the pinnacle. We've reached the functional group that's going to take the highest priority in nomenclature, which are carboxylic acids and their derivatives. So if you have OHs in there, if you have NHs in there, if you have ethers, those are all substituents, right, to the base carboxylic acid. So please remember that these always take highest priority. And so what changes when you're talking about the new functional group, right, is the suffix. So the suffix here is going to be oic acid with a space in between. So oic acid is our suffix for carboxylic acids. Okay? So if I just throw a whammy on the board here, if I had something like this, note that they're always terminal functional groups. So to be quite honest, you always, always, always have to give number 1 to the carbonyl carbon of the carboxylic acid, terminal functional group, right? So I'm at 1, 2, 3, 4, 5, 6. So this is a hexanoic acid, right? AN, because I have all single bonds. Oic acid's the end. At the 2 position, I have an oxo. Remember, keto groups are not taking priority over the carboxylic acid, so they're a substituent. They're oxos when they're substituents to the carboxylic acid. I have a chloro group, and I have a hydroxy, right? So those are my 3 substituents that I have here to my base carboxylic acid. So in this case, then, I'm going to alphabetize ahead of time, so this will be 4 chloro, 5 hydroxy, 2-oxo, and then hexane, and then oic acid, which is the suffix that's required for this. Yeah.
What if you have more than one carboxylic acid?
If you have more than one, then you dicarboxylic acid or tricarboxylic acid, but generally you won't see that. What you mostly likely will see in terms of all the reactions that we cover from henceforth are ones that have oxo groups and a carboxylic acid moiety. You don't generally see 2 carboxylic acids. But if you did, I guess with Michael additions you can, it would just be called dicarboxylic acid. They would obviously be your 2 end units, right? So the numbering isn't even necessary there, right? Yes?
So a carboxylic acid can never be in a ring?
So a carboxylic acid is never going to be in a ring. If it were, like, say something, you're thinking about having something like maybe like this. This is a lactone. This is actually an ester. So this is not a carboxylic acid. This is an ester. Specifically, these are, that should have a bond in there. These are called lactones. Carboxylic acids have to have an OH and not an OR. So there's no way to get that OH and still have it embedded in a ring, right? So that's something you don't have to worry about. Are there questions about nomenclature? Okay, so I do want to remind you, because we're going to, when I come in and I'm reviewing on Wednesday, I'm going to bring in some NMR. So I want to remind you just about the spectroscopy, right? Remember that this guy has an exchangeable hydrogen between 10 and 12 parts per million. This is one way spectroscopically to identify a carboxylic acid. Its IR also shows a carbonyl and an OH. It's a little bit harder to see because that OH doesn't really look like an OH in a carboxylic acid. And the reason is because the packing interactions of the carboxylic acids themselves. They use hydrogen bonding as their intermolecular attraction, their network, and hence they have these really crazy packing interactions which change the properties of that OH. So it makes it a little bit harder to see. If you've clued in and you see how carboxylic acids look with IR, that's a good thing. It will be helpful to you. I will bring one in and you'll see what I mean. It's up there. And so, yeah, it's right there. See?
Oh.
Now it actually looks cute. When it flies out, it's not so cute. Okay, so in this case, then, we're looking for that exchangeable proton. Okay. Now, there are I deserve more pay for this. Someone should email the president and tell them I am sweating up a storm. I need some, like, to sue the university for, like, just anguish or something. No, I'm only kidding. I'm not a legitimate person. Okay. So, in terms of carboxylic acids, there's a bunch of chemical reactions that about. Tell me the time. What time is it? 12:45?
12:24.
Video or something.
No, I'm leaving it. It's awesome.
No, like edited as in like compile the best parts.
Add a soundtrack.
Yeah, pretty much.
It's not going to eat you, Dr. Dixon.
You're trying me up here. We're just happy you're down there filming the damn thing.
Yes! Close the door! Close the door!
Open the door.
It went out.
It's like a bat. Is it going out?
It went out. It went out.
Now it's going to ambush you when you walk out the door.
You are a brave soul. I should give you extra credit for that.
Dr. Nixon, its nest might be there, it just could be, it could come back later, that's all. That's from the homework last night.
That's karma.
You keep laughing. That's how this is going to work, though. I tell my kids all the time, I always get the last laugh.
All laugh together.
No. It's always me. I get the last and final laugh.
Just remember, I'm voting on your Social Security.
You are voting on. I have so already realized that I'm not going to have any Social Security. I'm down with that. Right? It's all good. I'm going to do what you all do. I'm going to get myself a little site that says, contribute to Dr. Dixon's retirement fund. All my students that I've had over the years will contribute $1. I'll be good. Because I teach like 1,500 students a year, times 12 years now, and I've got a lot of years left, so I'll be good. I won't need Social Security. Here we go. Permanganate cleavage, right? We really got to draw this back to chemistry. Permanganate cleavage, number 1, right? Oxidation of alcohols.
Yeah.
So you take alcohols, obviously primary alcohols, be much more clear about that, and you can oxidize primary alcohols with either a manganese-based reagent or a chromium-based reagent. Don't forget you can stop, aldehydes also will oxidize to carboxylic acids. That's along our oxidative continuum here. These are reactions that you've seen before. Are there reactions that I'm missing that you've already seen how to get carboxylic acids? Anyone?
Personalis?
Okay, great. There's one new one. This is the new one in this chapter. And that is to take a Grignard and add CO2 followed by nice acid work up here. Okay? So that's the new reaction. It's pretty easy to do. So you can start from some Grignard, any Grignard. Here we can take benzene. We can brominate benzene. We can add magnesium and ether. And now we have a great Grignard, and we're about to make benzoic acid. Here we go. BBr2 and some Lewis acid catalyst, magnesium and ether. We have a Grignard, and now, lo and behold, is the last step. So I add in CO2, right? And CO2 is going to carbon nucleophile right at the carbon of CO2, of which there's only one, so there shouldn't be any worry here. And hence, we will get out now a carboxylate. This is called a carboxylate. We will be using this terminology, so I'll write it down. Carboxylate. Okay? And the carboxylate, when acidified, will give me, in this case, benzoic acid. Voila. This is a new reaction. You can create it from any alkyl halide. I chose bromobenzene, but you can do this from an alkane chain. You could do this from an alkene, right? Lots of different ways or different alkyl halides you can start with that will create when making a Grignard and adding CO2 that can give you carboxylic acids. So this is one new reaction that you know in terms of carboxylic acid formation. Okay? So in those reaction schematics that abound on your exams, right, you should be looking at all those preparatory reactions before you get into these ketones, aldehydes, and carboxylic acids. So you should be reviewing those, or else you'll be missing just a small scaffold of points out there right at the beginning of that schematic. Are there questions about this? Yeah?
Can we also go from an aldehyde to a carboxylic?
Yes, so that's what I said when I wrote out the primary alcohols. Don't forget that an aldehyde is on the continuum. So yes, aldehydes themselves can also do that. Remember that ketones cannot further oxidize. And there's actually one other caveat. I don't know if the hand raised here is to remind you. But that's a very special caveat, right? That if I take this and I add I do Friedel-Crafts alkylation, don't forget that any benzene that has a benzylic carbon with a single proton. So a benzylic carbon, that's what's attached to the benzene, right, with a single proton. Just one is enough to, in terms of cleavage, give me benzoic acid as well. Okay, so this is specifically to create benzoic acid, but benzoic acid is a carboxylic acid, so I'm just putting it up here.
So would those be considered just two equal, or would we,
These two?
Yeah, would we need
Yeah,
to
I
use
mean-
one in any certain?
No.
Okay.
No. They both are using Lewis acid catalyst, so if you had anything that's susceptible to that, you're done, right? To begin. All right? So they'll review the carboxylic acid forming reactions for you at the beginning of this chapter, and then they're going to start to elucidate some of the reactions that carboxylic acids can undergo. So that's what we're going to start with. Yeah?
So, like in lab, would a Grignard just react with carbon dioxide in the air?
So no, it's not enough carbon dioxide in the, I mean, yes, it would in essence, but there's not enough carbon dioxide in the air, right, unless you were to take your flask and breathe into it, right? I don't suggest that, though. Yeah. Don't do that. You know, I used my PhD advisor mouth pipetted, so he scared me. Oh, it's disgusting. Yeah, he used to store his meat in our freezer with radioactive phosphorus. That was also a good one. Okay. His deer meat, you know, because in Vermont they hunt a lot, so we should get, no.
That's hardcore.
Alrighty then. So the first reaction we're going to talk about is esterification. Really, as a framework, something that you should think about, because on Monday we'll be finishing up this unit and starting our review for the exam. So I just want to give you a think about this sort of stance, okay? We had that little table written up here a couple weeks ago, or last week, I guess it might have been. And I just want to remind you of this, right? We said that a carboxylic acid is on par with an ester, right? We sort of equated it in terms of its reactivity with an ester. And the reaction we're going to be talking about here is this one right here. This is esterification, okay? Note my reversibility arrow here, right? Esterification, fully reversible. And I would use some alcohol and acid to get in here, okay? Now, there are other members of this carboxylic acid family, right? We have an amide down here. This is very hard to do. So we're going to put a little X on that. The question is why? Why is that hard to do? Okay? And really the answer is acid-base chemistry. I want you to look at this. We are going to talk about it. I'll allude to it next class. But I'm trying to give you a framework of what we're trying to do here. So I can't really make amides with great success. I can make anhydrides to some success, but my anhydrides, truthfully, need to be symmetric. And not all anhydrides are not required to be symmetric. Okay? So note, this is a symmetric anhydride. Okay? A symmetric anhydride. This actually is also a reversible reaction that requires a little bit of acid. Okay? And the last reaction that is doable is the reaction to give me acyl chlorides. Okay? So acyl chlorides, okay, are up here, and this reaction is not reversible and requires thionyl chloride, that's what that says, SOCl2, and purity. So the acyl chlorides are easy to make. So if you pull out any book here that talks about carboxylic acids, the main reactions they're going to talk to you about are esterification, formation of esters, and the reaction with thionyl chloride, formation now of acyl chlorides. Some of them choose to talk about this anhydride, some of them choose to talk about this, but the bottom line is those are not efficient reactions, so we don't generally use them. So if I want to convert a carboxylic acid into any of these derivatives, I got to start somewhere in here and then sort of interconvert, which is what we're going to be talking about as we move into the next chapter. So these two main ones, with thionyl chloride and with the alcohol, are the two main ones you should focus on when you're studying for the exam. So esterification is called Fischer esterification, and Fischer esterification requires, as a start, a carboxylic acid reacting with an alcohol, so we can choose, say, propanol, and some innocuous acid, H2SO4. Remember, we use innocuous acids because HSO4 minus, its conjugate base, is not nucleophilic, but could still be used if we need to, right, to pluck off protons or whatever. It's still sitting around in solution. It doesn't count in our golden rule, right? We don't worry about HSO4 minus being there. We know that that has to be if we have H2SO4 in there. Okay, so in this case, the first step with a carboxylic acid is always going to be protonation of the carbonyl. This should be getting boring, right? Always, 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 which is what I'm saying. It's a good step to be able to get some points mechanistically. Protonation of the carbonyl. And I've made now a good electrophilic center, which is the whole point of this, okay, is to make a good electrophilic center, okay? Remember, what is is our other choice? This is a choice where I'm making a good electrophile and I'm using a weaker nucleophile, in this case, the neutral alcohol. What's my other choice?
Make the OH a good leaving group.
I can either have a good electrophile and an okay nucleophile, or I can have a good nucleophile and an okay electrophile, right? So if I tried to set up the reaction like that, if I tried to do that, let's think about how that would look and why that's not going to work. So why we bother with this crazy, fully reversible reaction. That would require, say, a carboxylic acid and something like methoxide. Is this going to do this reaction? Because this is just what you were purporting to me, right? Use a good nucleophile. This is a good nucleophile. Great nucleophile. This is an okay electrophilic center. Is this going to do this reaction?
It's going to pull the hydrogen off
It's
of
going
it.
to pull the hydrogen. It's going to do acid-base chemistry before anything else, right? So this is a no. This isn't going to happen. Okay? It's not going to happen the way you want it to happen, which is to attack that carbonyl center and start to create the ester. What you actually get out of this is a carboxylate and a protonated alcohol, right? These are your conjugate base and conjugate acids. That's nowhere near what you wanted, right? Now here's the problem. The carboxylate, this guy, is even worse electrophile, right? This was an okay electrophile. Someone tell me why this guy here is an even worse electrophile, so even if I had an excess methoxide, I'm never going to get what I want. What's wrong with that center there?
The double bond on the...
Yeah.
Delocation of the electrons.
Delocation of the electrons because of the negative charge. Are you going to ever have a good electrophilic center that's right next door to a negative charge? Never, right? So this is definitely a problem. So we can't actually do the mechanisms this way, which is why we always run these reactions in acid, because we're making a good electrophile and we're allowing these good or weak nucleophiles to sort of come in. So now I have nucleophilic attack. Okay, so here we are. It came in, it's neutral, so it now has a positive charge on it. Next step, be fast. Say it out loud. Come on, you're all saying it.
Deprotonate the...
Deprotonation. That's exactly right. All right, next step. Probability would dictate that one of these OH groups is protonated, right? I mean, I have a third possibility, right, of protonating the same oxygen I just deprotonated, and a higher probability of protonating one of these other guys. And it doesn't matter which one, okay? It doesn't matter which one. It's actually a really good exam level question. And it's actually, I've seen it on the MCAT too. The question is this: if I took and say labeled this guy, so I'm going to put a little asterisk here, I put a label on it. What that means is instead of that being normal oxygen 16, I make it something radioactive, so that I can track where it is through the course of an entire mechanism. The question is, will this ever come out as water? And the answer is yes, it will. This can come out as water, and this oxygen can come out as water. Will this oxygen ever come out in water? No, because it's always part of that OR group, right? Never part of the OH. So this is a really good sort of thinking level question, okay? If you have a hard time with that, we have a record here that you can go back and look at the lecture and see it. So it wouldn't matter which one I protonated, right? It's either or. So when I go and do that, I've chosen this one at this point in time. So now I have water, which is a good leaving group, and now it can leave. And when it leaves behind a carbocation, which is resonance stabilized. Okay? Oops, wrong arrow. Resonance stabilized. reached pretty much the end of the line. That resonance stabilization reforms the carbonyl for me, right? And I see that I've gotten to my final product, which is an ester. Whenever you take an alcohol and acid, it's called esterification for the mere fact that you're getting an ester out of the reaction. So all that's necessary at this point is to take something, anything. At this point, you have probably lots of different choices for deprotonation to get back your final ester product. Okay? So I get an ester out of this. Yeah?
Why wouldn't you get like a ketone or something? Like why would it just keep on attacking with OH?
Mm-hmm. I totally hear what you're saying. So we can look at that actually. That's a good question. So let's look at that guy. So if instead I go and I stop here, which is where I am at this point in time. So I am right here. You're saying, why can't another mole of alcohol come in here? Okay. So if we have another mole of alcohol come in here, okay, I have this, right? Possibility. So how do you think experimentally, because I don't doubt you, you're right, but how do I know that this isn't going to happen, or better yet, better question, how can I guarantee that this isn't going to happen, right, as opposed to stopping at this point? What could be our guarantee? Yeah?
Limiting the reagent.
Using a limiting reagent methodology, which is exactly what you would do. So it's a great question, but that sort of moves into the lab component, right? How do I ensure that this isn't going to form, you know, a second derivative here, okay? Certainly that can happen. These all sit in favor of the carbonyl forming, though. So this second addition, just equilibrium constant-wise, doesn't lay in your favor. But you wouldn't know that because mechanistically I see that it's a draw for any nucleophile that's in solution, okay? Are there other questions about this guy here? Okay. All right. On Monday, we're going to do the late remaining questions, and then we're going to move on. Okay? We're probably ending early. That's okay with me. I feel like I've had